All right, thank you. Welcome, everybody. Welcome to the first seminar of the semester. It's a great pleasure to welcome today Dr. Ronen Talmon from IIT Israel, from Technion, where he's an assistant professor in electrical engineering. He received his BA degree in math and computer science from the Open University in Israel in 2005, and his PhD degree in ECE from the Technion in 2011. And from 2000 to 2005, he was a software developer and a researcher at the technological unit of the IDF, the Israeli Defense Forces. And from 2005 to 2011, he was a teaching assistant in the Department of Electrical Engineering. And then from 2011 to 2013, he was a Gibbs Assistant Professor in Mathematics at Yale University. He was working closely also with Rafi Koifman, for those of you who know Koifman. He recently joined the Department of Electrical Engineering at the Technion. His research interests are generally in statistical signal processing, analysis and modeling, speech, biomedical signal and harmonic analysis, and diffusion geometry. And he's a recipient of the Erwin and Joan Jacobs Fellowship, the Andrew and Erna Fins Viterbi Fellowship, and the Horeb Fellowship. It's a pleasure to welcome Dr. Talmon. I had the pleasure of meeting him actually a few months ago back in Israel when I was visiting, and today he'll be talking about some of the research that he's been doing in dynamical systems and geometry. And thank you for coming. The floor is yours.
Thank you. Thanks for the introduction and the invitation. So actually the title of the talk is pretty long and scary. So instead of repeating it, I'm just going to start by presenting an application. So this is a biomedical application. Here the goal is to identify pre-seizure states in intracranial EEG, in epileptic patients from intracranial EEG signals. Intracranial means that the electrodes in this case are implanted in surgery in the patients. Now the problem in this application, or the challenge here, is that we have no ground truth, which means that even in the research community, in this research community of epilepsy, it's not clear whether such pre-seizure states exist, and if they exist, whether you can see them based on EEG signals. Now, what you can see here, what you can see here, I hope it's big enough.
It's the camera, it's not projector.
Yeah. I was just making sure. So I hope you can all see. What we have here is just an example of a signal. This is 35 minutes of EEG signal just before an epileptic seizure. Okay, so the seizure is happening here. Usually it is characterized by a very large amplitude, so it's easy to identify it based on the implanted electrodes. But as you can see here, based on the raw EEG signal, and I hope you can also see the Fourier spectrum, it's pretty hard to notice whether you have a trend that is happening before the seizure. And indeed, if you apply let's say roughly statistical tests on the different parts of this signal, it's hard to see a distinction between them. So our approach is a little bit different. What we want to do is build an intrinsic model or intrinsic geometry to the signal. That is, so the question is, what is intrinsic, right? So we define intrinsic as building a canonical coordinate system that is independent of the way that we measure things. We measure the physical phenomena, in this case, let's say the brain activity. So that's the end result of the analysis that I'm going to tell you about. What we do is process the EEG signal that I showed you before in short windows. For each window, we create an embedding. In this case, a three-dimensional embedding. So each point here is the three-dimensional embedding of every short window in time of the signal that I showed you before. Now, okay, so I claim this is intrinsic. It does not depend on the way that I measure things. But the real thing that we want to get from the intrinsic representation that we build is some kind of physical or physiological meaning. So that is the Holy Grail. And the question is how to do it. But in this case, I said that we don't have a ground truth. So what we did was to color the points based on the time to seizure. Okay, so what you can see here...
Excuse me.
Yes?
We're not seeing the presentation. Could you have your technician send content to us, please? Thank you.
Just go on.
So you can see here that the points are basically organized in the embedded domain according to the time to seizure. So even though just by observation we didn't see anything, any trend happening before the seizure, here we can clearly see it. So hopefully by building this intrinsic representation, we were able to extract or recover something of a real physiological meaning. So let me just simplify the problem a little bit, like really, really simplify it. What is intrinsic geometry, right? Let's say I'm given a bunch of points, right? Now I can write each point in the Cartesian coordinate system using the x and y coordinates. I can also decide to write it in a spherical coordinates, right? In this case, using the radius and the angle, right? What is the point of intrinsic geometry or intrinsic coordinate system? No matter if you give me the points described in the Cartesian coordinates or in the spherical coordinates, I want to give you a canonical description that is...
Is your resolution set to 1024 by 768? That might be the problem why I'm not seeing it.
I have no idea.
Looks okay.
Can you ask if they're seeing it now?
Do you see it now?
I can see it now. Thank you.
Okay, great. Okay, so what is intrinsic geometry? A simple case. We can represent each point in the Cartesian coordinates or spherical coordinates. The point of intrinsic geometry is that we want to create a new coordinate system that is independent of the way that we represented the points. So, but not only that, right? We also want to we said that we also wanted to have some sort of physical or physiological meaning. In this case, it means that if you can notice that those points lie on a circle, right, we would like our canonical representation to have a notion of that. For example, in this case, we would probably want it not to be two-dimensional, but just one-dimensional, right? So that is the general idea. And the analogy of this, to what I showed you before, is that the way that I choose to represent the points, the coordinate system, is basically the measurement, right? This is the type of the sensor that I'm using, the exact place that I'm implanting my electrode, and so on. What I want to get is something more abstract, right? I want to get let's say the brain activity, or something that is canonical. And no matter how I measure it, I want to get the same thing. Now, it seems to be a too difficult task to do, so what we are doing is relaxing the problem a little bit. First of all, we will construct the new coordinate system through the solutions of eigenvector problems in the framework of manifold learning, and it will allow us to only find a metric, a local metric, between the measurements instead of solving the entire problem and creating the entire coordinate system. The second thing is that the solution applies only to time series, and we are going to use dynamics in order to build this canonical coordinate system. So if I want to generalize the problem or write it in a most general way, I would write like this. Let's say I'm getting measurements z of t. What I want to get is the intrinsic hidden variables that control the measurement. I'll call it theta of t. And the goal is from z of t, in an empirical way, recover or extract theta of t. And like I mentioned before, what we are going to focus on is finding a metric, a distance metric between a pair of measurements. That will give us a notion of a distance between what we want, between the samples, the corresponding samples of the hidden variables theta. Now, in the EEG, Z is the EEG signal. Theta is, like I said, the unknown brain activity. So I'm also going to use dynamical systems vocabulary. So just to make the analogy, you can think of Z, the signal, as the output of an unknown dynamical system that changes with time. This dynamical system is controlled by an intrinsic state. So you can think of it like a knob that we can configure. This is the configuration of the system. And this is basically what we want, because the output of the signal can be highly influenced by a lot of sources of variability and also by an unknown input, but this is not of interest. The thing that we want, that characterize the system, is its configuration, its intrinsic state. So this is the way we are going to treat it and borrow a few terms from dynamical systems. One thing in particular that I'm going to talk a little bit more about it later is the notion of observation. Because like I said, the signal and also the output of the dynamical system can be influenced by a lot of sources of variability that are not necessarily related to the intrinsic state that I'm looking for. For example, it can be measurement noise. Now, so if you think of the simple geometry example, that might move my points away from the circle, right? So what I want to do is look for an observer that I will call phi that will get rid or be invariant to all those irrelevant sources of variability. So the way that we write it is that phi of Z gives us a vector of observations, or a vector of observations for the measurements, or you can think of it as features or descriptors that better, I would say, in the observation, you can better see the intrinsic state that you are looking for, or it is more related, and we'll define it exactly. So now we can really divide what we want to do into two parts. First part, given good observations, what we want to do is find the intrinsic state. And then or before that, we would need to find a good observers to the system or to the signal. Okay, so what we are proposing also has two parts. The first part is going to be based on local analysis. Here we are going to find this local metric by learning the metric. That gives us a notion of a distance between what we are looking for. This is what I'm going to focus on. The second part, the global part, is going to be based on standard manifold learning. We'll build the kernel, do the standard analysis, and get a parameterization of the unknown intrinsic state or intrinsic variable. Now, at this point, just as a background, I want to mention principal component analysis, or PCA, because it's somewhat similar to what we are trying to do. So in PCA, the idea is that we are getting high-dimensional points, Z. We are looking for a global and linear projection matrix, W, such that in the embedded points, theta, we preserve maximal power. Right? Now, we know that the solution of this problem is given by the eigenvectors of the empirical covariance or correlation matrix of the data Z. Geometrically, it means that if we have a cloud of points Z, I hope you can see it, the eigenvectors of the covariance matrix of the data identify the principal directions that we have in the cloud. So in a minute, I'll show how it is related to what we want to do. But in our case, we have a little bit different setting. We have a trajectory in time, now of observations, phi of Z. Now, if we just look in a short window of time, we can think of the trajectory or the samples here as the same cloud of points that now respect the tangent plane to the manifold that we are looking for, or to the manifold where our intrinsic process is. So we can conceptually apply a local PCA on this cloud of points, identify the directions of this cloud of points, and that will give us, at least locally, the principal directions of the tangent plane to the manifold. Okay? So how do we actually do it? So for each point in time, or for each time index t, we look at a sampling grid around it. Then what we do is a local linearization of the observation using just the first order Taylor expansion. Right? So k here is the first order term, it's the Jacobian of the observation, but the observation is with respect to the unknown parameter theta. So nothing here we can actually compute. And then we have all the higher order terms and also the estimation error. Now, if we use the same PCA assumption here locally, that in fact the covariance of the underlying state, or the covariance of the samples of the underlying state have unit variance. And by the way, this is where the dynamics is taken into account. This is an assumption on the dynamics of the intrinsic state or the underlying variable that we are looking for. And this is what is going to help us define the canonical, to find the canonical coordinate system that I'm going to show in a minute. So under this assumption, we can end the local linearization. If we compute the empirical covariance of our observations, we can show that it equals the Jacobian times the Jacobian transpose plus an error, a small error. Consists of all the higher order terms. So this is very, very significant. Why? Because we have access to the empirical covariance of the observations, right? We see that it gives us information on the mapping of the intrinsic state to the domain of observation, right? Where the intrinsic state is unknown and also the mapping is unknown, right? So empirically, we can get a lot of information on this unknown intrinsic process that we want, right? Based on something that we measure without knowing anything. Now, in this work, we use this information to define a metric. So the metric we use is called the Mahalanobis metric. It's, again, a distance between a pair of measurements that is defined by the distance between the observations under normalizing it or subtracting the local mean of each observation, and then weighting the coordinates according to the pseudo-inverse of the empirical covariance. Okay? So that is almost the standard form of the Mahalanobis distance. The formula is not really important. What is important is that we have here a distance between things that we have access to. This is one thing. And another thing is that we use local information that is stored in the covariance matrix. And this, like I said, is the encoding of the dynamics into the system. Now, what was shown is that this distance, the Mahalanobis distance defined this way, approximates the Euclidean distance between the associated samples of the unknown hidden process or intrinsic process to the second order. Okay? So this is almost like magic in a sense, right? We don't know what we are looking for. Just by a very simple assumption that we have unit variance of the change of our intrinsic process, we cannot get access to the process itself, but we can get access to the Euclidean distances between the samples of that process. Now, just to give a little bit more intuition about it, the way that we see the Mahalanobis distance is an empirical way to build invariance. Now, in this case, what is going on? It's a little bit different story from what I showed 2 slides ago. What we have here is this. We have a parametric manifold. This is where the intrinsic hidden process lives. Right? What we said is that if we look at a short window in time around a certain sample, we get a cloud of samples. And our assumption was that this cloud of samples has unit variance. So geometrically, it's like a round ball. Now we measure this process and maybe also apply an observer. Right? What we get in the measurement domain or observation domain is that this round cloud of points is distorted. Right? Now, this is what we get, but we can identify this cloud of points because this is just a short window in time of samples, right? And then when we compute the covariance, right, we can identify the shape of that cloud, and then we compute a pseudo-inverse. It's like the inverse, right? So we contract the shape back to a circle, right? So we go back to this, what we call unknown, but canonical domain of intrinsic processes, right? So it doesn't matter how we distort those round cloud of points, we always recover this domain. So it's like an anchor for us, a canonical coordinate system. So let me show you a result on a toy problem. Let's say I have a 2D torus, two torus in 3D, and a Brownian motion on that torus, and I sample it. Okay, so that's the samples of my underlying state or my underlying process. Now I decided to measure this process using the standard parametrization of the process. So for each 3D point here, I get the 2 angles of the torus here. Okay, so this is my measurement domain. I don't know really what I had at the beginning. Okay, so that's all I'm getting. Okay, so the exercise here would be to take a pair of points, compute the Mahalanobis distance based on the covariance matrices, and the claim is that it approximates the Euclidean distance. So here is what we get using the approximation. What you see here in the x, so we picked a point, and then we computed distances from that point to all the other points. So what you see here in the x-axis is the Euclidean distance in the original unknown domain of the torus. What we have here in the y-axis is the Mahalanobis distance, computed based on the measurements, and this is just the Euclidean distance between the measurements. Okay? So this is what we compute. This is what we don't have access to. Now, as you can see, the Mahalanobis distance, at least locally, right, if we bound it by 1, so at least locally the Mahalanobis distance gives us a pretty good approximation of the unknown Euclidean distance in the original domain. Now, if I just skip forward a little bit, if I use this distance and apply a standard manifold learning technique, I can recover the torus. Now, at least for me, it looks really like magic, right? So there is something that I didn't tell you here, right? Because otherwise, it's not possible. What is that? Because how come I can start with this, right? A 2D picture, and I can get a torus, right? It doesn't make any sense. So why I didn't tell you here that it's not exactly true that I have 2D samples, right? What I have here is a trajectory, right? And my assumption is that this trajectory came from the torus. And I know that on the torus it was a Brownian motion. And here I know how to identify those ellipses, right? Those clouds. So that is the dynamics that allowed me to basically, from this picture and the fact that I have a trajectory, recover the torus. Okay? So I also want to show you a statistical interpretation for the same thing. Let's say now, in addition, that my samples of the underlying process are Gaussian, and also the observations given the underlying state or the underlying process is also Gaussian. Under those statistical assumptions, Tipping and Bishop showed that the Mahalanobis distance approximates the Euclidean distance between the MMSE estimators of the underlying state. Okay? So this is just a statistical notion of the approximation that we get to theta or statistical approximation that we get of theta to the underlying intrinsic state based on the metric. Now, it also supports the search for Gaussian observers. So I'm going to talk in a minute of how can we choose an observer that is going to fit this framework. But this shows that we would like to have a Fourier-like observers that integrates or sums a lot of samples, right? So we will get something that is close to Gaussian, so this will be true. And then we have a guarantee that our estimation is really good also in a statistical way. Okay, so up to now we saw the local analysis. Now we have the global part, where we take the local metric and integrate it. So what I have here is a standard manifold learning algorithm. So if we get measurements z of t, the first thing is to build a pairwise affinity kernel based on, in this case, a Gaussian with the Mahalanobis distance instead of the standard Euclidean distance. The reason that a Gaussian kernel is usually used is because it defines a sort of locality, right? Because if you have 2 points with distance that is more than the scale of the Gaussian, it's almost negligible, right? So you only take you take into account only points that are relatively close. And then in this algorithm, the standard practice is to normalize it. I won't go into details, but then take the normalized kernel, apply eigenvalue decomposition, get eigenvectors, and then use the eigenvectors in order to build the embedding. So for each point, we'll have its embedded point using the values of the corresponding eigenvectors. So for us, it all will also be an inverse map. Yes?
Good question. How do you choose that small d, how big the embedding is going to be? Is that learned somehow?
You mean at
No, I mean in your when you're creating the d.
Oh, the dimension.
The dimension, yes.
Okay, I will talk about it. It's a great question. I don't think anyone knows how to do it properly. There's no closed solution. There are many ways. I will show one. Because that is basically d here. I mean, we have to estimate d. What for me d is the dimension, the true dimension of theta, which I don't know. Right? I have to estimate. This is like the number of sources of variability that I have in my problem. The way that I'm going to approach it is through the observer, because like I said, the observer can separate the sources of variability that I want, that I call intrinsic, and the sources of variability that I don't want. So that is how we will use it here. Okay, so just one last thing. Here we also see it as an inverse map, right? We see the embedding as a representation of our new coordinate system or our underlying process. Okay, so I talked a lot. I just wanted to put here the algorithm just to show you that it's really simple. So we have 7 steps. I'll go over it very quickly. What we need is to compute the observations, then take short time windows, compute the covariances. From there, we have the metric, build the kernel, apply eigenvalue decomposition, get the eigenvectors, and that's it. Now, this is our embedding. So this is like 7 steps, and it's almost 7 lines in MATLAB.
And of course, the interval, time interval also
is important.
Is a parameter of choice.
Yeah, that's true. It's actually very significant. I didn't put it here in the presentation, but right now we also have a pretty good analysis of what we want from that time analysis, or from that time interval. I will say that I will say this. Right? I think that what I showed here, most of the analysis relies on the assumption that in the intrinsic domain we have a round ball of points. It comes from actually a physical model of a diffusion process. that you have a driving Brownian motion. So what we want is that your drift to change slowly enough in your short window in time such that you will only see the Brownian motion and get such a round cloud of points. So this is the analysis. So in fact, you're right. So what we are going to get here is only a coarse version of the underlying process, or I would say a slower version of it, because we use time frames. Okay, now going back, so that's the algorithm. We applied it to the EEG signal, and this is the results. These are the results that we get. Let me first focus on the second row. What we have here is the embedding of two recordings that are coming from two different electrodes before the same seizure. Now this is what I showed you before. This is from a different electrode. Basically you can see the same trend. I remind you that this is the 3D embedding, and the color here represents the time before the seizure. Okay, so you can see a clear trend. But you can also say, okay, this result might be very trivial, right? Because what you do is you identify time, and you have time, right? So we also applied it to a third electrode that was located far away from the seizure onset area. So this electrode shouldn't really see anything related to the seizure, and in fact, if we do the analysis and then color the points according to time, we don't see any trend. Now, regarding the observer, what we tried is using the standard Fourier spectrum as an observer and a new transform that is called scattering transform that was proposed, I think it's here, yeah, was proposed by Mala 2 years ago. Now, as you can see, we can only see the trend using the scattering transform. However, using the Fourier spectrum, we don't see anything. Right?
So the pattern that you're seeing there before seizure, is that also validated across other measurements where you had no seizure at all?
Yes.
In other words, over time,
yes.
Not only over space.
Yes. I mean, by the way, here there is nothing over space. This is just over time. We have.
You said that, for instance, the third component is a spatially sort of an uncorrelated component,
yes,
rather than temporally uncorrelated.
Right. So yes. Yes, I mean, I just presented here. This is an example because I thought it would be more indicative, but maybe it's not. I mean, if you take a part of the recording that comes, let's say, a day before the seizure, you would get essentially the same result as this one. I should also say that we tried that. I mean, this is a relatively short database. We had, I think, between 6 and 7 patients, and each patient had around 6 episodes. I think it's between 5 and 7, and the results are pretty similar.
For this type of shape?
No, not that I know of.
Medical point of view?
Not that I know. It's really hard to do because there is really no ground truth. We were happy to see that we could get an organization of the point according to, or something that is indicative to the fact that we are going to have a seizure in 30 minutes or 15 minutes, but we couldn't really add more to it, at least at this point. Okay, so the question that I want to answer now is why, or try to understand why the scattering transform worked and why the Fourier transform didn't work. And so it brings us to the question, what is a good observer to the data, especially in light of, or if we want to use it in a manifold learning framework. So we are going to use dynamical system vocabulary. So we'll define observability. I'm not going to go over the details. The basic idea is that if we have a small perturbation of the underlying samples, what we want to do is to be able to detect it in our observations. Right? So we want it to be bounded from, we want this distance to be bounded from below. On the other hand, we also define stability. It means that if we have a small perturbation in our intrinsic state, we don't want to see a very large perturbation in our observation. Right? Now, if I combine those two conditions, I can just say that I want my observation operator or observation function to be a bi-Lipschitz function with respect to theta, right? To the intrinsic state or intrinsic variable. Now, again, I'm not going to go over the details, but I also have the part of the invariance, right? If I have a lot of sources of variability, I might want to get rid of some, right? Because they are irrelevant. So I can also define invariance of my observation with respect to other sources of variability that are not my theta. Okay, so that was just a definition. How can we actually test whether an observer has these properties? So the way we do it is, again, through the covariance. Right? What did we show based on our assumption on the dynamics? We showed that the empirical covariance is the Jacobian times the Jacobian transpose of the Jacobian of the observation operator, basically, right? Between the observations and what we don't know, theta. So it tells us a lot of things. One thing it tells us is that the rank of the covariance is the dimension of theta, the dimension of the unknown thing. So first of all, we can use that, right, in order to set or in order to see whether we have a good approximation of the covariance, right? Because this is empirical, or in order to determine what is the dimension of the unknown theta. So that is. This is. Sorry. Okay. So this is one thing. The other thing is that it also gives us a very tight relationship between the eigenvalues of the empirical covariance and the singular values of the Jacobian, right? Because the eigenvalues of the empirical covariance are the square of the singular values of the Jacobian. So I'll talk to this. I'll touch in the next slide, but before that, this is just an empirical way to show what basically you asked me before, but usually it is done based on the spectrum of the kernel. What we do here is do this test based on the spectrum of all the local covariances, and this is also a way for us to design the observer and to see whether we have a good approximation of the covariance. So what I'm talking about is that if I look at the spectrum of all the local covariance matrices, what I want to see is such an elbow. So I want to see these significant eigenvalues and then a plateau or something, because this basically should represent 0. And it also shows me how invariant I am to all the nuisance sources of variability that I have in my data. Okay. So this is this. But going back to the eigenvalues, singular values thing, if I use the local linearization, I can actually rewrite the observability and stability condition just based on the first order derivative, the Jacobian. So the constant, so what I want is to be bounded from below and from above by the two constants that I defined before. Now, in this case, I know that the two constants are given to me by the smallest and largest singular values of the Jacobian matrix, right? But as I said before, I have access to it through the eigenvalues of the local covariance, right? So what I can do is take the eigenvalues of the local covariance. For example, look at the ratio between them. That would give me an approximation to the ratio between B and A, and I will know how tight I am or how regular my observation is with respect to theta, even if I don't know what is theta, right? So what I want it to be, so if I look at if I examine this ratio and I see that it's fairly close to 0, I know that my observer is very irregular, right? On the other hand, if I see that it's close to 1, I know that it's very regular, almost identity. So my goal would be to design or to choose an observer with a ratio that is as close as possible to 1. Now, when we tried it on the EEG data, this is the result that we get. What we have here is the ratios So since we don't really know what is the dimension, we just try. So this is the ratio between the first and the second, the ratio between the first and the third, and the first and the fourth, and so on. And we plot the ratio as a function of time. That's the ratio that we get based on the Fourier analysis, and there the ratio that we get based on the scattering transform. And as you can see, the ratio based on the scattering transform is closer to 1 and much more stable, right? Which shows us that this is basically a better observer to this specific data than the Fourier transform, and this is probably one of the reasons why this works and this doesn't. Okay, so using this framework, we also wanted to analyze different observers a little bit further. So we looked at 3 observers. One was histograms, which is quite popular in computer vision and image processing, and the Fourier transform and the scattering transform, and to see what makes an observer good. So let me first comment about histograms. And histograms, at least in our case, they have a very nice property. Right? If I can write my measurement as an important part or an interesting part plus a noise, right, with an additive noise, then what I know is that in the density domain, the density of my measurements are given just by a convolution between the density of the interesting part and the density of the noise. Why is that important? Because this is just a linear operator, right? The effect of the noise is a linear operator on what I'm looking for. Now, what I know is that the Mahalanobis distance is invariant to linear operation. Right? So ideally, if I could get, using histograms, a good approximation of the density, I know that I'm completely invariant to measurement noise. So that's a great plus. The downside is that it's very difficult to estimate histograms, especially based on time series, especially based on high-dimensional time series. So this is why we went to more standard solutions. So the most standard, I guess, is the Fourier spectrum. Again, I'm not going to go over the definition, but I'm just going to say that this is very convenient because we can compute it very efficiently. But the problem that we identified is that the Fourier, and by the way, also it gives us something that is Gaussian-like, which is good for us. But the problem is that it is unstable to deformation. And we believe that deformation, specifically time deformation, is something that is very spread in natural, real signals that we get. So let me explain a little bit more about that. So let's say that my measured signal is a signal that underwent a time deformation. Right? So at every point in time, I stretch or contract my time axis in a random way according to my theta, which now controls the way that I deform the signal. Right? So if I, again, use linear approximation, I can write the time deformation as a translation and scaling. Now, if I apply the Fourier transform and takes just the spectrum, just the absolute value, right, it is invariant to the translation, but I get the scaling. So the bottom line is this. Even if my distortion is very small in time, it can be very big in high frequencies. Right? So it says that the Fourier spectrum is not stable with respect to time deformation. Right? Now we can also test this based on the partial derivatives of the spectrum. So again, I don't want to get into details, but if you take the ratio between the partial derivatives, one with respect to time and one with respect to the frequency, you take the integral of the log of that ratio, you can show that you have some kind of constant plus the log of the frequency. So in fact, this is something that we can compute empirically because we have the spectrum and we can try to approximate the partial derivative. So if we have time deformation, this should behave or go linearly with the log of the spectrum. The log of the frequency. Okay, so now we also have an empirical way to know whether we have time deformation. So the way that we should work is that given a signal, we apply the Fourier transform, see if we have time deformation. If we don't, it would probably work. If we have, we need to do something else. What is this something else? The scattering transform that was proposed by Malat 2 years ago. And I'm not going to get again into details, but it can be shown that this transform that is roughly based on a wavelet transform is stable with respect to time deformation. So let me show you an example. Okay? What we have here is what we call a time-warped or a time-distorted autoregressive process. So X is just a simple autoregressive process with the coefficient theta 1. Okay, so theta 1 controls basically the shape of the spectrum of this process. So this is a standard process. And then this process undergoes time deformation controlled by theta 2. So here, theta has two coordinates, one controlling the autoregressive process, the other one controlling the time deformation. Our goal is getting Z, right, the measurement, which is the distorted autoregressive process, try to recover theta 1 and theta 2. Now, okay, so I'm going to skip this or go over it very, very quickly. You can actually show that if we choose the Fourier spectrum as an observer, it is by Lipschitz with respect to theta 1, but with respect to theta 2, as we said before, it's unstable, so it's not Lipschitz. This is the result of the empirical test that I showed you before to test whether we have time deformation on this process. So as you can see, we have a fairly straight linear line with a slope of 1. If we observe this integral as a function of the log of the frequency, so it shows that we have time deformation as we do. And this is the result of the algorithm. So what do we have here? First of all, this is the spectrum, the eigenvalues of the kernel. Okay? So what it shows is that we have only one significant source of variability. And now what we do here is here we plot the principal component, the principal eigenvector that we get as a function of theta 1. This is the ground truth that we didn't have. And this is the second eigenvector as a function of theta 2. Now we also tried all the combinations. What you can see is that the first eigenvector recovers pretty nicely theta 1, what controls the autoregressive process. But in terms of time deformation, we couldn't really recover it. Okay? Why? Our guess is that because the Fourier transform is not stable to it. So we see that we don't see we just see one source of variability. On the other hand, if you compare this to what we get from the scattering transform, so first of all, based on the spectrum, you can see that we see more sources of variability. And also, now if we take the second eigenvector as a function of the time deformation, you can see that we have a pretty nice correspondence that shows that we were able to detect, maybe not in the most accurate way, but at least something.
Does it have to do with the fact that, because here underlying all these ideas, that there is the rate at which your parameters, the underlying parameters are varying, because otherwise there's no way.
Right.
There's no way to recover them.
Right.
So the rate at which they're varying is slow enough for your time interval, basically.
Exactly. This is also what I wanted to answer you for your previous question. But it applies to both sources of variability. Right? So both sources of variability in this case have the same rate.
So I think basically the reason your scattering thing works better, or your scattering transform works better, is because you're using wavelets, and wavelets have that.
So I don't think so.
You don't?
We thought of that, but in this case we used exactly the same frames for the Fourier analysis and the wavelet analysis. So I think that specifically here, in the difference here, this is not the reason, because in both cases, both theta 1 and theta 2 had exactly the same rate, and underwent the same analysis with the same length of windows. I think, but what you are saying is completely true. I mean, this is a basic assumption that we need to see the variability or the perturbations of our underlying process inside the window. And if it's going to change a lot, we are going to see too many things and then our assumption won't hold. Okay, so I have 5 more minutes. I wanna show you another biomedical application, and this application is about sleep stage identification. It's fairly similar to the first EEG application that I showed you. Here we have, I mean, this is for people who have sleep disorder. They go to special clinics or sleep laboratories, and then what they do there is that they measure a lot of things. Among them is EEG, but this time scalp EEG, placed outside, and also the respiratory activity by measuring the airflow, and also muscle activity from the chest and abdomen. And the goal here is to identify the known 6 sleep stages: awake, REM, it's called a rapid eye movement, and non-REM, which varies between shallow and deep sleep. So that's the type of mission. Here is just one example to the result that we could get, basically based on the same analysis. What you can see here is an example for the EEG signal that we have. So what are we doing? Again, processing in short time frames. Each time frame, we apply our observer, in this case, the scattering transform. Then, based on the measurements, we calculate the Mahalanobis distance. And then, from that, we can build the kernel, get the embedding. And what you can see here is the 3-dimensional embedding that we get. And the color here now represents the 6 different stages of sleep. Now, as you can see, we get quite a nice clustering of the embedded points based on the sleep stage that we didn't use in advance, or that we didn't know in. Yeah, the colors. Okay, so this is just a summary of the result. This study was a little bit bigger than the other one. We had a full night of 10 patients. What you can see here is the result of the analysis for each of the 10 patients. We measure the sensitivity and specificity, but for me the nice thing here is actually the different curves. But you can see, I don't know if you can see, but the dark gray curve is the result that we get based on the EEG signal. The light gray curve is the result that we get based on the respiration signal, and the black curve is the result that we get based on both. Now, why for me that is a nice result? First of all, because we can see that we can get a fairly reasonable result based on each of the measurement, but also the fact that we were able to build a canonical coordinate system for each of the measurements, even though they are completely different. EEG and respiration, like airflow, are completely different. The fact that we were able to build a canonical coordinate system allowed us to combine them easily because they live in the same coordinate system, and then get an improved result. So I just want to thank my collaborators, Rafi Koifman, Stefan Mala, Iten Zaveri, Houtin Wu, and Roy Lederman. And thank you.
We have time for some questions, maybe 2 or 3 questions. Yes.
I have a basic question. Just I don't understand after you change the data from the principal component analysis result to the geometric space, why do you consider the time deformation?
Why do I consider time deformation?
Yeah.
I mean, the time deformation was just an example. So we have to separate between the way that I created the signal in a simulation and I use the time deformation, and the way that we do the analysis. Right. So when I do the analysis, I don't know anything. I mean, I don't assume anything specific about the time deformation. I just apply the algorithm. I hope I'm answering.
Especially for those examples, right?
So the time deformation was just a special case that I wanted to show that the scattering transform is a better observer because it is stable, and otherwise if I'm getting an observer that is not stable, I'm not going to get a good result.
Have kind of a basic one. So the faster your process is, the smaller the time window you will need, right?
Yes.
So, and I would guess the number of samples you need in that time window would be enough so that your covariance matrix is accurate.
Exactly right. What I have here, and this is probably in practice, this is the most significant thing that I need to care about in this kind of analysis, is this trade-off. If I would ideally want to use small time frames because I want to get a better time resolution. On the other hand, in using small time frames, I don't have a lot of samples, so my estimation of the empirical covariance would be pretty bad.
Yes, please.
I've got a couple of questions. One's practical. Because EEG signals are very small, they're amplified and introduce a lot of noise. Did you compensate for that, or do you know if that was compensated for as you took the signals?
Yes. So that was that. So the intracranial EEG that we use was a little bit pre-processed before we use it by basically removing the artifacts and the outliers. Yeah.
The second question is, what about your Jacobian? Did you ever test it to the extent that it lost rank so that you couldn't map between one variable and the other? It becomes singular.
Oh, so this is, so I think that it's always singular, right? I mean, the singularity of the covariance is by definition. Why? Because usually the dimension of the measurement is larger than the dimension of the intrinsic state that I'm looking for. So if that would write on the board?
Try to write it. Yeah, try to. I don't know if
It won't write with the laptop.
Oh, it won't write with the laptop.
Okay. So anyway, the covariance matrix. Let's say the dimension of my measurement is n. So the covariance matrix, the dimension is n by n.
Right.
The Jacobian, and let's say the dimension of my intrinsic variable is d. So the Jacobian is n by d, right? So I know that, and let's say that d is less than n. So the covariance, right, is n by m, but of rank d. So it's by definition singular. So this is why in practice, or not only in practice, but also the way that we define the Mahalanobis distance is not the standard way, but we use the pseudo-inverse of the covariance.
I have one question. Could you then reinterpret, because the whole time you were talking, the one thing that keeps coming back to my mind, this is almost like a deconvolution problem, and then the question that I had was, have you looked at the robustness of your estimator in terms of the whiteness, your assumed whiteness of
my underlying
of your perturbation, and also maybe the normality of that perturbation?
Yes. So I think that now we have actually not a full but some analysis to that. The assumption that the way that I presented the assumption here was fairly empirical, I would say, because all we need, and this is the same assumption that we have when we do PCA, right? Is that we assume that what we are looking for uncorrelated coordinates. So this is and if they are Gaussian, it's basically the same assumption. It comes from physics. It comes from the model of diffusion that you have a drift and then a driving Brownian motion. So if your drift is slow, all you see is the perturbation of the Brownian motion, and if your coordinates are independent, then you get this round cloud of points. So you are right. I mean, it's not always the case in practice. But the good thing about this is that the entire approach is data-driven and unsupervised. So even if our system is not like that, we are going to get the best fit that with those assumptions to the data that we have. So according to my experience, based on these applications and others, it works pretty well.
Ronen, isn't it sufficient for us to assume that the underlying process is on a manifold? Then you can say you can always find such a chart which is orthogonal.
I'm not sure. I think that, let's say it this way. If you assume that you have independent intrinsic variables, then yes. If they live on a manifold, then you need to assume that locally on your manifold they are independent.
But I can define my independent variables to be that.
Right. I mean, if you do that, then fine. I mean, if you control the notion of locality, you can always define that, and then yes. But then in practice, we have the problem of maybe in the locality that we define, we don't have enough samples.
Remember, he's trying to get the intrinsic coordinates. Yeah. You have a question? No? All right, let's thank our speakers.
Thank you.